Geothermal energy is the thermal energy in the Earth's crust that originates from the formation of the planet and the radioactive decay of materials. The high temperature and pressure in Earth's interior cause some rock to melt and solid mantle to behave plastically. This results in parts of the mantle convecting upwards since it is lighter than the surrounding rock. Temperatures at the core mantle boundary can reach over 4,000 degrees C, 7,200 degrees F. Geothermal heating, using water from hot springs, for example, has been used for bathing since Paleolithic times and for space heating since ancient Roman times. More recently, geothermal power, the term used for the generation of electricity from geothermal energy, has gained in importance. It is estimated that the Earth's geothermal resources are theoretically more than adequate to supply humanity's energy needs, although only a very small fraction is currently being profitably exploited, often in areas near tectonic plate boundaries. As a result of government-assisted research and industry experience, the cost of generating geothermal power decreased by 25% over the 1980s and 1990s. More recent technological advances have dramatically reduced costs and thereby expanded the range and size of viable resources. In 2021, the U.S. Department of Energy estimates that geothermal energy from a power plant built today costs about $0.05/kWh. In 2019, 13,900 megawatts (MW) of geothermal power was available worldwide. An additional 28 gigawatts of direct geothermal heating capacity has been installed for district heating, space heating, spas, industrial processes, desalination, and agricultural applications as of 2010. Forecasts for the future of geothermal power depend on assumptions about technology, energy prices, subsidies, plate boundary movement, and interest rates. Pilot programs like HEB's Customer Opt-in Green Power program show that customers would be willing to pay a little more for a renewable energy source like geothermal. About 100,000 people are employed in the industry. The adjective geothermal originates from the Greek roots I circumflex cubed a inverted question mark, G-A tilde superscript A, meaning earth, and a circumflex cedilla I circumflex micro I diaresis I circumflex 1/4 I ami, term A tilde cubed S, meaning hot. Hot springs have been used for bathing at least since Paleolithic times. The oldest known spa is a site where the Hualqinkai Palace was later built. In the 1st centuries, Romans conquered Aquisulas, now Bath, Somerset, England, and used the hot springs there to feed public baths and underfloor heating. The admission fees for these baths probably represent the first commercial use of geothermal power. The world's oldest geothermal district heating system in Chaudes, France, has been operating since the 15th century. The earliest industrial exploitation began in 1827 with the use of geyser steam to extract boric acid from volcanic mud in Larderlo, Italy. In 1892, America's first district heating system in Boise, Idaho was powered directly by geothermal energy and was copied in Klamath Falls, Oregon in 1900. The first known building in the world to utilize geothermal energy as its primary heat source was the Hot Lake Hotel in Union County, Oregon, whose construction was completed in 1907. A deep geothermal well was used to heat greenhouses in Boise in 1926. And geysers were used to heat greenhouses in Iceland and Tuscany at about the same time. Charlie Lee developed the first downhole heat exchanger in 1930 to heat his house. Steam and hot water from geysers began heating homes in Iceland starting in 1943. In the 20th century, the electricity demand led to the consideration of geothermal power as a generating source. Prince Pirojine Orhai tested the first geothermal power generator on July 4, 1904, at the same Larderlo dry steam field where geothermal acid extraction began. It successfully lit 4 light bulbs. Later, in 1911, the world's first commercial geothermal power plant was built there. It was the world's only industrial producer of geothermal electricity until New Zealand built a plant in 1958. In 2012, it produced some 594 megawatts. In 1960, Pacific Gas and Electric began the operation of the first successful geothermal electric power plant in the United States at the Geysers in California. The original turbine lasted for more than 30 years and produced 11 megawatts net power. The binary cycle power plant was first demonstrated in 1967 in the USSR and later introduced to the US in 1981. This technology allows the generation of electricity from much lower temperature resources than previously. In 2006, a binary cycle plant in Chena Hot Springs, Alaska, came online, producing electricity from a record low fluid temperature of 57 degrees C. 135 degrees F. In 2021, Quaise Energy announced the idea of using a gyrotron as a boring machine to drill a hole 20 kilometers in depth and use it to produce geothermal energy. The technique would use frequencies of 30 to 300 GHz and would transfer energy to a rock 1 trillion times more efficiently than using a laser. Lasers would further be disrupted by the vaporized rock, which would affect the longer wavelength much less. Drilling rates of 70 meters appear to be possible with the 1 megawatt gyrotron. The Earth's internal thermal energy flows to the surface by conduction at a rate of 44.2 terawatts (TW), and is replenished by the radioactive decay of minerals at a rate of 30 TW. These power rates are more than double humanity's current energy consumption from all primary sources, but most of this energy flow is not recoverable. In addition to the internal heat flows, the top layer of the surface to a depth of 10 meters, 33 feet, is heated by solar energy during the summer, and releases that energy and cools during the winter. Outside of the seasonal variations, the geothermal gradient of temperatures through the crust is 25 38 degrees C, 45 54 degrees F. per km of depth in most of the world. The conductive heat flux averages 0.1 megawatts/km2. These values are much higher near tectonic plate boundaries where the crust is thinner. They may be further augmented by fluid circulation, either through magma conduits, hot springs, hydrothermal circulation, or a combination of these. The thermal efficiency and profitability of electricity generation are particularly sensitive to temperature. The most demanding applications receive the greatest benefit from a high natural heat flux, ideally from using a hot spring. The next best option is to drill a well into a hot aquifer. If no adequate aquifer is available, an artificial one may be built by injecting water to hydraulically fracture the bedrock. This last approach is called hot dry rock geothermal energy in Europe, or enhanced geothermal systems in North America. The much greater potential may be available from this approach than from conventional tapping of natural aquifers. Estimates of the potential for electricity generation from geothermal energy vary sixfold, from 0.035 to 2 TW depending on the scale of investments. Upper estimates of geothermal resources assume enhanced geothermal wells as deep as 10 kilometers, 6 miles, whereas existing geothermal wells are rarely more than 3 kilometers, 2 miles, deep. Wells of this depth are now common in the petroleum industry. The deepest research well in the world, the Kola Super Deep Borehole, is 12 kilometers, 7 miles, deep. Geothermal power is electrical power generated from geothermal energy. Technologies in use include dry steam power stations, flash steam power stations, and binary cycle power stations. Geothermal electricity generation is currently used in 26 countries, while geothermal heating is in use in 70 countries. As of 2019, worldwide geothermal power capacity amounts to 15.4 gigawatts, GW, of which 23.86% or 3.68 gigawatts are installed in the United States. International markets grew at an average annual rate of 5% over the 3 years to 2015, and global geothermal power capacity is expected to reach 17.6 gigawatts by 2020. Based on current geologic knowledge and technology the G publicly discloses, the Geothermal Energy Association, (GE), estimates that only 6.9% of total global potential has been tapped so far, while the IPCC reported geothermal power potential to be in the range of 35 gigawatts to 2 TW. Geothermal energy is a key renewable source that covers a significant share of the electricity demand in countries like Iceland, El Salvador, Kenya, the Philippines, and New Zealand, and more than 90% of the heating demand in Iceland. Geothermal power is considered to be a sustainable, renewable source of energy because the heat extraction is small compared with the Earth's heat content. The greenhouse gas emissions of geothermal electric stations are on average 45 grams of carbon dioxide per kilowatt-hour of electricity, or less than 5% of that of conventional coal-fired plants. As a source of renewable energy for both power and heating, geothermal has the potential to meet 3 to 5% of global demand by 2050. With economic incentives, it is estimated that by 2100 it will be possible to meet 10% of global demand. Geothermal electric plants were traditionally built exclusively on the edges of tectonic plates where high-temperature geothermal resources are available near the surface. The development of binary cycle power plants and improvements in drilling and extraction technology enable enhanced geothermal systems over a much greater geographical range. Demonstration projects are operational in Landau Falls, Germany, and Sault-Suze for 8 France, while an earlier effort in Basel, Switzerland, was shut down after it triggered earthquakes. Other demonstration projects are under construction in Australia, the United Kingdom, and the United States of America. In Myanmar, over 39 locations are capable of geothermal power production, and some of these hydrothermal reservoirs lie quite close to Yangon, which is a significant underutilized resource. Geothermal heating is the direct use of geothermal energy for some heating applications. Humans have taken advantage of geothermal heat this way since the Paleolithic era. Approximately 70 countries made direct use of a total of 270 pj of geothermal heating in 2004. As of 2007, 28 gigawatts of geothermal heating capacity is installed around the world, satisfying 0.07% of global primary energy consumption. Thermal efficiency is high since no energy conversion is needed, but capacity factors tend to be low, around 20%, since the heat is mostly needed in the winter. Geothermal energy originates from the heat retained within the Earth since the original formation of the planet, from the radioactive decay of minerals, and solar energy absorbed at the surface. Most high-temperature geothermal heat is harvested in regions close to tectonic plate boundaries where volcanic activity rises close to the surface of the Earth. In these areas, ground and groundwater can be found with temperatures higher than the target temperature of the application. However, even cold ground contains heat, below 6 meters, 20 feet. The undisturbed ground temperature is consistently at the mean annual air temperature, and it may be extracted with a ground source heat pump. Geothermal energy comes in either vapor-dominated or liquid-dominated forms. Lardrolo and the geysers are vapor-dominated. Vapor-dominated sites offer temperatures from 240 to 308 degrees C that produce superheated steam. Liquid-dominated reservoirs, LDRs, are more common with temperatures greater than 208 degrees C, 392 degrees F, and are found near young volcanoes surrounding the Pacific Ocean and in rift zones and hotspots. Flash plants are the common way to generate electricity from these sources. Pumps are generally not required, powered instead when the water turns to steam. Most wells generate 2 to 10 megawatts of electricity. Steam is separated from a liquid via cyclone separators, while the liquid is returned to the reservoir for reheating, reuse. As of 2013, the largest liquid system is Cerro Prieto in Mexico, which generates 750 megawatts of electricity from temperatures reaching 358 degrees C, 662 degrees F. The Salton Sea field in Southern California offers the potential of generating 2,000 megawatts of electricity. Lower temperature LDRs, 128 to 208 degrees C, require pumping. They are common in extensional terrains, where heating takes place via deep circulation along faults, such as in the western US and Turkey. Water passes through a heat exchanger and a Rankine cycle binary plant. The water vaporizes an organic working fluid that drives a turbine. These binary plants originated in the Soviet Union in the late 1960s and predominate in new US plants. Binary plants have no emissions. Enhanced geothermal systems, EGS, actively inject water into wells to be heated and pumped back out. The water is injected under high pressure to expand existing rock fissures to enable the water to freely flow in and out. The technique was adapted from oil and gas extraction techniques. However, the geologic formations are deeper and no toxic chemicals are used, reducing the possibility of environmental damage. Drillers can employ directional drilling to expand the size of the reservoir. Small-scale EGS has been installed in the Rheingraben at Soltsus for 8 superscript ATS in France and Landau and in Schaim in Germany. Geothermal power requires no fuel, except for pumps, and is therefore immune to fuel cost fluctuations. However, capital costs are significant. Drilling accounts for over half the costs, and exploration of deep resources entails significant risks. A typical well doublet, extraction and injection wells, in Nevada can support 4.5 megawatts MW, and costs about $10 million to drill, with a 20% failure rate. As noted above, drilling cost is a major component of a geothermal power plant's budget and is one of the key barriers to the wider development of geothermal resources. A power plant must have production wells to bring the hot fluid, steam or hot water, to the surface and must also have injection wells to pump the liquid back into the reservoir after it has passed through the power plant. Drilling geothermal wells are more expensive than drilling oil and gas wells of comparable depth for several reasons. Geothermal reservoirs are usually in igneous or metamorphic rock, which is harder than the sedimentary rock of hydrocarbon reservoirs. The rock is often fractured, which causes vibrations that are damaging to bits and other drilling tools. The rock is often abrasive, with high quartz content, and sometimes contains highly corrosive fluids. The formation is, by definition, hot, which limits the use of downhole electronics. Casing in geothermal wells must be cemented from top to bottom, to resist the casing's tendency to expand and contract with temperature changes. Oil and gas wells are usually cemented only at the bottom. Because the geothermal well produces a low-value fluid, steam or hot water, its diameter is considerably larger than typical oil and gas wells. In total, electrical plant construction and well drilling cost about a negation to a $5 million per MW of electrical capacity, while the break-even price is 0.04 a 0.10 a negation per kWh middle.h. Enhanced geothermal systems tend to be on the high side of these ranges, with capital costs above $4 million per MW and break-even above $0.054 per kWh middle.h. In 2007, the capital cost of one such district heating system in Bavaria was estimated at somewhat over $1 million a negation per MW. Direct systems of any size are much simpler than electric generators and have lower maintenance costs per kWh middle.h, but they must consume electricity to run pumps and compressors. Some governments subsidize geothermal projects. Geothermal power is highly scalable, from a rural village to an entire city, making it a vital part of the renewable energy transition. The most developed geothermal field in the United States is the geysers in Northern California. Geothermal projects have several stages of development. Each phase has associated risks. At the early stages of reconnaissance and geophysical surveys, many projects are cancelled, making that phase unsuitable for traditional lending. Projects moving forward from the identification, exploration, and exploratory drilling often trade equity for financing. Geothermal power is considered to be renewable because any projected heat extraction is small compared to the Earth's heat content. The Earth has an internal heat content of 1031 joules, 3 a middle.1015 TWh, approximately 100 billion times the 2010 worldwide annual energy consumption. About 20% of this is residual heat from planetary accretion. The remainder is attributed to past and current radioactive decay of naturally occurring isotopes. For example, a 5,275 meters deep borehole in United Downs Deep Geothermal Power Project in Cornwall, England, found granite with very high thorium content, whose radioactive decay is believed to power the high temperature of the rock. Natural heat flows are not in equilibrium, and the planet is slowly cooling down on geologic timescales. Human extraction takes a minute fraction of the natural outflow, often without accelerating it. According to most official descriptions of geothermal energy use, it is currently called renewable and sustainable because it returns an equal volume of water to the area where the heat extraction takes place, but at a somewhat lower temperature. For instance, the water leaving the ground is 300 degrees, and the water returning is 200 degrees. The energy obtained is the difference in heat that is extracted. Current research estimates of the impact of heat loss from the Earth's core are based on a study done up through 2012. However, if household and industrial uses of this energy source were to expand dramatically over coming years, based on a diminishing fossil fuel supply and a growing world population that is rapidly industrializing and requiring additional energy sources, then the estimates on the impact on the Earth's cooling rate would need to be re-evaluated. Geothermal power is also considered to be sustainable thanks to its power to sustain the Earth's intricate ecosystems. By using geothermal sources of energy, present generations of humans will not endanger the capability of future generations to use their resources to the same amount that those energy sources are presently used. Further, due to its low emissions, geothermal energy is considered to have excellent potential for the mitigation of global warming. Iceland has so much geothermal energy that even the sidewalks in Reykjavik are heated with it. In winter, this saves the need for gridding. Even though geothermal power is globally sustainable, extraction must still be monitored to avoid local depletion. Over decades, individual wells draw down local temperatures and water levels until a new equilibrium is reached with natural flows. The three oldest sites, Lardurlo, Wairaki, and the geysers, have experienced reduced output because of local depletion. Heat and water, in uncertain proportions, were extracted faster than they were replenished. If production is reduced and water is re-injected, these wells could theoretically recover their full potential. Such mitigation strategies have already been implemented at some sites. The long-term sustainability of geothermal energy has been demonstrated at the Lardurlo field in Italy since 1913, at the Wairaki field in New Zealand since 1958, and at the Geysers field in California since 1960. Falling electricity production may be boosted through drilling additional supply boreholes, as at Poihipi and Oaiki. The Wairaki power station has been running much longer, with its first unit commissioned in November 1958, and it attained its peak generation of 173 megawatts in 1965, but already the supply of high-pressure steam was faltering, in 1982 being derated to an intermediate pressure and the station managing 157 megawatts. Around the start of the 21st century it was managing about 150 megawatts, then in 2005 to 8 megawatt size pentane systems were added, boosting the station's output by about 14 megawatts. Detailed data are unavailable, and being lost due to reorganizations. One such reorganization in 1996 causes the absence of early data for Poihipi, started 1996, and the gap in 1996-7 for Wairaki and Oaiki. Half-hourly data for Oaiki's first few months of operation are also missing, as well as for most of Wairaki's history. Fluids drawn from the deep earth carry a mixture of gases, notably carbon dioxide, CO2, hydrogen sulfide, H2S, methane, CH4, and ammonia, NH3. These pollutants contribute to global warming, acid rain, and noxious smells if released. Existing geothermal electric plants emit an average of 122 kilograms, 269 pounds, of CO2 per megawatt hour, MWA of electricity, a small fraction of the emission intensity of conventional fossil fuel plants. But a few plants emit more than gas-fired power, at least in the first few years, such as some geothermal power in Turkey. Plants that experience high levels of acids and volatile chemicals are usually equipped with emission control systems to reduce exhaust. In addition to dissolved gases, Hot water from geothermal sources may hold in solution trace amounts of toxic elements such as mercury, arsenic, boron, and antimony. These chemicals precipitate as the water cools, and can cause environmental damage if released. The modern practice of injecting cooled geothermal fluids back into the earth to stimulate production has the side benefit of reducing this environmental risk. Plant construction can adversely affect land stability. Subsidence has occurred in the Werrikei field in New Zealand. In Stoffen-Imbriske, Germany, tectonic uplift occurred instead, due to a previously isolated anhydrite layer coming in contact with water and turning into gypsum, doubling its volume. Enhanced geothermal systems can trigger earthquakes as part of hydraulic fracturing. The project in Basel, Switzerland was suspended because more than 10,000 seismic events measuring up to 3.4 on the Richter scale occurred over the first 6 days of water injection. Geothermal has minimal land and freshwater requirements. Geothermal plants use 3.5 square kilometers, 1.4 square miles, per gigawatt of electrical production, not capacity, versus 32 square kilometers, 12 square miles, and 12 square kilometers, 4.6 square miles, for coal facilities and wind farms respectively. They use 20 liters, 5.3 US gal, of freshwater per MWA middle.h versus over 1,000 liters, 260 US gal, per MWA middle.h for nuclear, coal, or oil. The Philippines began efforts in researching geothermal energy in 1962 when the Philippine Institute of Volcanology and Seismology inspected a geothermal region in Tiwi, Albay. The desire in shifting to geothermal energy was due to the worldwide oil crisis in the 1970s. These efforts led to the construction of the first geothermal power plant in the Philippines in 1977, which is located in Tongganan. Late. The development of the geothermal plant in the Tongganan field was made possible due to the drilling contract with the New Zealand government in 1972. The Tongganan geothermal field, TGF, advanced in growth by adding plants such as Upper Mayao, Matlabog, and South Sambalaran, which resulted in producing 508 megavolts in the area. By 2008, the TGF was recognized as one of the world's most developed geothermal power plants. As research in geothermal energy progressed, the first geothermal power plant in the Tiwi region operated in 1979 and 2 other plants followed the area in 1980 and 1982. The Tiwi geothermal field is located about 450 kilometers from Manila, which is on Luzon Island and the country's capital. The 3 geothermal power plants in the Tiwi region were producing 330, which allowed the Philippines to be next behind the United States and Mexico in geothermal growth. The geological location of the Philippines resulted in volcanic activity, which is a source of geothermal energy, and it became an advantage since it provided resources to further the research. The Philippines has 7 geothermal fields and continues to contribute efforts in utilizing geothermal energy by creating the Philippine Energy Plan 2012 to 2030, aiming to achieve utilizing 70% of geothermal energy by 2030. According to the Geothermal Energy Association, installed geothermal capacity in the United States grew by 5%, or 147.05 megawatts, since the last annual survey in March 2012. This increase came from 7 geothermal projects that began production in 2012. GE also revised its 2011 estimate of installed capacity upward by 128 megawatts, bringing the current installed U.S. geothermal capacity to 3,386 megawatts.